Welcome! In this session, we'll dive into an interesting problem titled Minimum Non-Zero Product of the Array Elements. We'll explore its requirements, constraints, and potential approaches to solve it. Let's get started. The problem involves finding the minimum non-zero product of an array of integers, which is derived from powers of 2. Specifically, you're given a positive integer p, and the array nums contains all integers from 1 to 2 p1. Your task is to select elements from this array such that their product is minimized, while ensuring the result is not 0. Finally, you must return this value modulo 10 plus 7 to handle potentially large results. The input consists of a single integer p, which can range from 1 to 10 to the power of 7, and the output is the minimum non-zero product as a single integer. For example, if p is given as 1, the array nums contains just one element, 1. Since there is only one element to choose from, the minimum non-zero product is simply 1. Taking this modulo 10 plus 7 does not alter the result, so the output is 1. On the other hand, when p is 2, the array nums expands to 1, 2, 3. Here, the minimum non-zero product is calculated by multiplying all the elements together. 1 * 2 * 3 equals 6. Again, taking modulo 10 plus 7 leaves the result unchanged, so the output is 6. Now, consider the case where p is 3. The array nums grows to 1, 2, 3, 4, 5, 6, 7, and the challenge becomes more complex. To minimize the product, we must carefully select a subset of numbers while balancing the contribution of smaller and larger elements. By following the optimal strategy, the minimum non-zero product is calculated as 1512. As always, the result is returned modulo 10 plus 7, so the output remains 1512. This example highlights the importance of finding an efficient method to compute the result, especially as the array size increases exponentially with p. Finally, it's important to note the constraints and considerations for solving this problem. The answer must always be returned modulo 10 plus 7, which helps prevent overflow during calculations with large numbers. As p can go up to 10 the size of the array nums grows exponentially, making it impractical to compute the product directly for large p. Optimized algorithms are crucial to handle such cases efficiently. Additionally, edge cases include the smallest input, where p equals 1 results in an array with just one element, and the largest input, where p equals 10 results in a massive array. Ensuring the use of modulo operations at every step is essential for maintaining accuracy and complying with the constraints. To solve the problem of finding the minimum non-zero product of the array elements, one initial approach we might consider is brute force. The intuition here is straightforward. We explicitly generate the array nums, which contains all integers from 1 to 2 p1. Then, we calculate the product of all possible combinations of these elements to determine the minimal non-zero product. However, there are some key observations that reveal why this approach is not feasible. First, the size of the array grows exponentially with p. For instance, if p is 15, the array has 32,767 elements. Computing the product for such a large array is computationally prohibitive. Additionally, the values involved in these computations can grow so large that they exceed the limits of standard integer operations, leading to overflow. For these reasons, while simple to understand, the brute force approach is rejected as impractical for larger values of p due to its exponential time complexity and the risk of computational limits being breached. Recognizing the limitations of brute force, we turn to a more sophisticated, optimized mathematical approach. The key insight here is that we don't need to explicitly construct the array to solve the problem. Instead, we can analyze its mathematical structure to simplify the computation. Here's how we break it down. The largest element in the array is 2 p1, followed by sequentially smaller numbers down to 1. By observing this pattern, we realize that the product of these numbers can be partitioned into smaller, manageable pieces. To avoid the risk of overflow, we utilize modular arithmetic, which allows us to compute results modulo 10 to the power of 9 plus 7. The steps of the solution are as follows. First, we pair the largest element, 2 p1, with its complement to minimize the product. We then use modular exponentiation to efficiently compute the powers required for the calculation. The formula we derive is max underscore element, asterisk, base caret, count 1, % mod, where base is max underscore element 1 and count is 2 caret, p1, 1. This approach ensures that we compute the result efficiently, scales well for large values of p, and avoids the need to explicitly construct or iterate through the array in its entirety. The optimized mathematical approach, centered on modular arithmetic, is the strategy we ultimately chose. This method leverages the inherent structure of the array to avoid explicit computation while maintaining efficiency. By focusing on mathematical properties like modular arithmetic, exponentiation, and the symmetry of the array, we significantly reduce computational overhead and handle large values of p effectively. When comparing the two approaches, the brute force method is conceptually simpler but computationally infeasible for larger values of p due to its exponential growth and risk of overflow. On the other hand, the optimized approach is more mathematically involved, but it scales well, ensures correctness, and adheres to computational constraints. This trade-off is worthwhile, as the chosen strategy allows us to solve the problem efficiently, even for large inputs, while avoiding unnecessary complexity or the pitfalls of brute force calculations. The problem asks us to find the minimum non-zero product of all elements in an array nums that contains integers ranging from 1 to 2 caret p1. Since the size of this array grows exponentially with p, directly computing the product is impractical for large values of p. To solve this, we use mathematical properties to simplify the calculations. One key insight is the symmetry of the array around its maximum value, 2 caret p1, which allows us to identify patterns in the product. Additionally, by leveraging modular arithmetic, we can efficiently handle the large numbers that arise during computation, ensuring our results fit within computational limits. These insights form the foundation for our approach to solving this problem efficiently. To solve the problem, we start by defining constants, such as mod equals 10 to the power of 9 plus 7, which is used to manage large numbers through modular arithmetic. Next, we identify key values. The maximum value in the array, max underscore val, is 2 caret p1, and the second largest value, second underscore max, is derived as max underscore val 1. The size of the array is 2 caret p1. The array can be conceptually divided into two parts, the maximum value, which appears only once, and the remaining elements, which are symmetric around second underscore max. To minimize the product, the strategy involves repeatedly multiplying second underscore max for half the size of the array, excluding the max underscore val. Modular exponentiation is then applied to efficiently calculate second underscore max raised to this power, modulo mod. After computing the power of second underscore max, the next step is to combine it with max underscore val to get the final product. By multiplying the result of second underscore max caret size // 2 with max underscore val, and then applying modulo mod, we ensure the product remains within computational limits. Finally, we return this result as the answer. The algorithm is straightforward and works directly with integers and modular arithmetic, without requiring additional data structures. Two critical operations make this approach efficient: modular exponentiation for calculating powers in logarithmic time and modular multiplication to handle large numbers. These operations ensure that the algorithm is both time-efficient and space-efficient. The time complexity of this algorithm is dominated by modular exponentiation, which operates in O log n time, where n is the exponent. Since the exponent is proportional to 2 caret p, the overall complexity simplifies to O p. The space complexity is O(1), as the algorithm only uses a constant amount of space for intermediate calculations. The optimized algorithm involves computing the key values step by step, determining max underscore val equals 2 to the power of p1, finding second underscore max equals max underscore val 1, calculating the exponent as size // 2, and then using modular exponentiation to compute the power of second underscore max. Finally, the result is obtained by multiplying this power with max underscore val and taking the modulo. This step-by-step approach ensures both correctness and efficiency. For a concrete example, consider p equals 3. The array spans from 1 to 2 caret 3, 1 equals 7. Here, max underscore val is 7, and second underscore max is 6. The exponent, calculated as size // 2, is 3. Using modular exponentiation, we compute 6 caret 3% mod, which equals 216 since it is less than mod. Multiplying this result by max underscore val, we get 216 by 7% mod equals 1512. Thus, the output is 1512. For edge cases, when p equals 1, the array contains only 1, so the product is 1. For large values of p, modular arithmetic ensures that computations remain efficient and avoid overflow. The algorithm also correctly handles both even and odd-sized arrays, leveraging their symmetry to simplify calculations. This code solves LeetCode problem number 1969, minimum non-zero product of the array elements. The problem requires finding the minimum non-zero product of all elements in an array nums ranging from 1 to 2 p1, modulo 10 9 plus 7. Explanation. 1. Pre-computations and modular arithmetic. The constant mod is set to 10 9 plus 7 to handle large numbers efficiently. The helper function mod_exp calculates modular exponentiation using an iterative approach. This ensures that even for large exponents, we compute results efficiently in O, log, exp, time. 2. Core logic. The largest number in the array, max_number, is calculated as 1p1, equivalent to 2 p1. To minimize the product, we leverage the fact that the array can be grouped into max_number and max_number1 repeated product_count times. Here, product_count equals max_number1 //2. 3. Efficient computation. Using modular exponentiation, we calculate max_number1 raised to product_count modulo mod, reducing computational overhead. The final result is obtained by multiplying this power with max_number modulo mod. 4. Return result. The result is returned as the minimum non-zero product modulo 10 9 plus 7. This approach ensures efficient handling of the exponential growth of nums for large p, achieving logarithmic complexity for the modular exponentiation. This is the Java implementation of LeetCode problem number 1969, minimum non-zero product of the array elements. The logic mirrors the provided Python solution, with adjustments for Java's type system and syntax. Key differences include explicit type declarations, the use of a helper method for modular exponentiation, and the use of long to handle large values during calculations. The code calculates the minimum non-zero product by breaking down the problem into modular arithmetic operations. The problem requires us to compute the minimum non-zero product of elements in an array consisting of all integers from 1 to 2 to the power of p1, while ensuring the result is taken modulo 10 9 plus 7. This involves handling very large values efficiently, which is why modular arithmetic becomes crucial. The key insights here include identifying that the largest number in the sequence is max_number, calculated as 2 to the power of p1. To minimize the product, we strategically pair numbers to reduce their combined contribution, and this leads us to the formula. Max_number1, product_count times max_number, mod, 10 to the power of 9 plus 7. The term, max_number1, product_count is calculated using modular exponentiation, which allows us to handle very large powers without overflow, ensuring the computation is both correct and efficient. To illustrate the solution, let's consider the case where p equals 1. Here, the largest number in the sequence is max_number equals 1 equals 1, and the number of terms contributing to the product_count, is calculated as max_number1 / 2 equals 0. Since product_count equals 0, the term max_number1 product_count simplifies to 0 which, by convention, equals 1. Using modular arithmetic, the result is computed as result equals power_mod times max_number mod equals 1 by 1 mod 10 to the power of 9 plus 7 is equal to 1. Therefore, the output for this example is 1. Now, let's look at the next example where p equals 2. Here, the largest number in the sequence is max_number equals 1 equals 3, and the number of terms contributing to the product is product_count equals max_number1 / 2 equals 1. Using modular exponentiation, we calculate the term max_number1 product_count as mod underscore exp 2 1 mod, which simplifies to 2. This efficient computation ensures that even with larger values, we avoid overflow and stay within the bounds of modular arithmetic. Once we have the result of the modular exponentiation, the final result can be calculated. For this example, the formula becomes result equals power underscore mod times max underscore number mod. Substituting the values, we get result equals 2 by 3 mod 10 to the power of 9 plus 7, which equals 6. Hence, the output 4p equals 2 is 6. Next, 4p equals 3, the largest number becomes max underscore number equals 1 3 1 equals 7, and the product underscore count is max underscore number 1 / 2 equals 3. This increases the complexity of the computations, but the approach remains the same. To compute the required result 4p equals 3, we begin by calculating max underscore number 1 caret product underscore count using modular exponentiation. The term mod underscore exp 6 3 mod evaluates to 216 as we compute 6 by 6 by 6 mod step by step to avoid overflow. Finally, substituting into the formula, the result becomes result equals 216 by 7 mod 10 to the power of 9 plus 7, which equals 1512. This demonstrates how the solution uses the structure of the sequence and modular arithmetic to handle large values efficiently. The overall approach ensures correctness and scalability, even as p increases, by leveraging the formula and modular exponentiation to minimize overflow risks while maintaining computational efficiency. When analyzing the time complexity of our solution for problem number 1969, we start by breaking down each component. First, calculating max underscore number is straightforward. The expression 1p 1 uses a bitwise shift, which is a constant time operation, or O1. Next, product underscore count is computed as max underscore number 1 / 2, which also involves basic arithmetic and is therefore another O1 operation. The most computationally intensive part of the solution is modular exponentiation, implemented in the mod underscore exp function. This function calculates max underscore number 1 caret product underscore count % mod using the efficient method of exponentiation by squaring. The time complexity of modular exponentiation is proportional to the number of bits in product underscore count. Since product underscore count grows roughly as 2 caret p1, the number of bits is proportional to p, making this step OP. To complete the analysis, we look at the final multiplication and modulo operation, or result equals power underscore mod asterisk max underscore number % mod. This step simply involves basic arithmetic and is an O1 operation. Combining all these steps, the dominant factor in the time complexity is the modular exponentiation, which runs in OP. Therefore, the overall time complexity of the solution is OP. Now, turning to space complexity, the algorithm uses only a constant number of variables, including max underscore number, product underscore count, power underscore mod, and result, all of which require O1 space. Additionally, the mod underscore exp function is implemented iteratively, meaning no extra stack space is consumed. There are also no auxiliary data structures used in the algorithm. As a result, the space complexity of the solution is O1. To put this into perspective, let's compare our optimized solution with the naive approach. A brute force method would involve explicitly constructing the array of 2 caret p1 elements and then calculating the product of all non-zero elements. This would require O2 to the power of p multiplications, which becomes computationally infeasible for large p-values like p equals 60 due to the exponential growth. In contrast, the optimized solution cleverly avoids constructing the array. By leveraging mathematical properties in modular arithmetic, we reduce the problem to modular exponentiation, which has a much more manageable time complexity of OP. This is a significant improvement over the naive approach. Finally, we can mathematically confirm the big O complexity of the mod underscore exp function, which performs O log product underscore count iterations. With product underscore count approximately equal to 2 caret p1, this simplifies to OP. Since the other operations are O1, the total time complexity is dominated by the modular exponentiation step, resulting in OP. The space complexity remains O(1), as no extra memory is allocated beyond the constant number of variables used in the solution. When tackling this problem, there are a few common mistakes that candidates often make. First, using a brute force approach for large inputs can quickly become computationally infeasible. For instance, if p is as large as 60, generating all permutations or subsets results in exponential time complexity, which is simply not practical. Instead, you need to look for mathematical simplifications or optimized algorithms. Another frequent issue is ignoring modular arithmetic. When working with very large numbers, such as the products of arrays with large elements, it's easy to encounter overflow errors or unnecessary computational overhead. To avoid this, always check if the problem specifies a modulo constraint, like 10⁻9 plus 7, and apply modular arithmetic accordingly. Lastly, misinterpreting the problem statement is a surprisingly common pitfall. For example, confusing minimum non-zero product with minimum product might lead you down the wrong path entirely. Always take care to clarify subtle constraints and edge cases, such as arrays with a single element or extremely large inputs, to ensure your solution aligns with the problem requirements. Another mistake candidates make is overcomplicating simple patterns. Problems involving powers of 2, like 2⁻p, often have inherent mathematical properties that can drastically simplify the solution. Overlooking these patterns and trying to solve the problem in a more complex way can waste valuable time. It's also important to handle edge cases thoroughly, such as when the array contains only one element or when the result is the product of just two numbers. Ignoring these cases can result in runtime errors or incorrect outputs. Now, when it comes to interviews, recognizing patterns is key. Powers of 2 often exhibit logarithmic or exponential properties, and symmetry or repetitive patterns can provide clues for simplifying the solution. Always optimize early. If you see constraints like a large p, immediately discard brute force and explore mathematical or modular arithmetic-based approaches. Communication is equally important. Clearly explain your thought process to the interviewer, emphasizing why certain methods like brute force are suboptimal and what trade-offs you're making with your optimized approach. Finally, take time to practice modular arithmetic, as it's a recurring concept in problems involving large numbers. Techniques like modular exponentiation can be invaluable in these scenarios. Understanding related problems can also help you approach this challenge more effectively. For instance, LeetCode problems like 1498, 1759, 1621, and 1862 all involve mathematical patterns, constraints, or optimizations that might be useful here. By studying these, you'll gain a broader perspective on how to tackle similar challenges. In terms of alternative approaches, mathematical simplification is one of the most powerful tools at your disposal. Instead of brute force, focus on recognizing the structure of the problem. For example, if the array nums contains all numbers from 1 to 2⁻p1, the product can often be expressed as a function of p, which can then be reduced using modular arithmetic. This requires deeper insight but is far more computationally efficient. Another approach involves binary representation and bit manipulation. Since problems involving powers of 2 are closely tied to binary operations, leveraging bitwise techniques can greatly simplify calculations. However, this approach might feel less intuitive to some, especially under the pressure of an interview. Understanding the trade-offs between these methods will help you decide the best approach for the given constraints. Divide and conquer is another strategy to consider. This involves breaking the problem into smaller, more manageable subproblems. For example, you might split the array into halves, solve for each half recursively, and then combine the results. While divide and conquer is generally more efficient than brute force, it's still less optimal compared to direct mathematical solutions, especially when dealing with very large values of p. This is because even recursive solutions can introduce unnecessary overhead when a more elegant mathematical approach exists. Ultimately, the key is to understand the trade-offs and choose a method that balances efficiency with simplicity, ensuring your solution is both correct and computationally feasible for the given constraints. Thank you for staying with us. We've summarized the key points of the problem and the approaches considered. Remember to practice modular arithmetic and optimize your solutions for large inputs. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!